Hello, this video attempts to explain Lagrangian mechanics in a way that hopefully strikes a right balance between intuition and rigor. At the heart of Lagrangian mechanics is this widely used Euler-Lagrange equation, originally derived from D'Alembert's principle and much later shown to follow from the principle of least action by Hamilton. Mathematically, principle of least action is based on a very powerful tool called calculus of variations, and so I would like to start off with the calculus of variations problem, which will lead nicely to Lagrangian mechanics. The problem goes like this. Mr. Lagrange is hired to drive his steamroller along a 5-kilometer track within 1 hour. The fee during the 1 hour period is $60 per hour, where x is the distance from the starting point. The fuel cost is $3v² per hour, where v is the speed of the steamroller. Find the maximum profit that Mr. Lagrange can possibly earn. The income is integral 60x dt from 0 to 1 hour. The expense is integral 3v² dt from 0 to 1 hour. The profit is income minus expense, which is integral 60x minus 3v² dt from 0 to 1 hour. In this video, we will use a dot notation over a symbol to denote time derivative. So for x being a position function, x dot, which is dx by dt, would be a velocity function. So we can just replace v with x dot. The number 60 in the income formula can be moved out of the integral sign, same as the number 3 in the expense formula. Now, if the graph of x looks like this, the graph of x dot would look like this. And the graph of x dot squared like this. The income is 60 times the green area, and the expense is 3 times the purple area. The profit is 60 times the green area minus 3 times the purple area, and this is what we need to maximize. What is the curve of x that maximizes the profit? A straight line or parabola perhaps, maybe a graph of polynomial or trig or exponential functions, or elliptical or cycloidal arc. There are endless possibilities and one can be overwhelmed by where to start. To get going, let's warming up by looking at a couple of special cases first. Special case 1. Mr. Lagrange drove at one speed for the first half hour and another speed for the second half hour. Considering the two options of the blue and the pink curves, which one you think will result in higher profit? You can pause the video to think about it. Well, it can be observed that both options have the same expense, since the speed in the first half of the blue curve is the same as the speed in the second half of the pink curve, and also the other way around. However, since the area under the pink curve is larger than the area under the blue curve, the pink option would have higher income and higher profit. So, to maximize the profit, the speed in the first half has to be higher than the speed in the second half. But how much higher? Let's try out some numbers. If x1 dot is double x2 dot, we get profit of $91.67. If it's triple, the profit is up to $93.75. Quadruple, and it's down to 93. It seems that the profit is maximized around 93.75. Let's find the exact value. The income is 60 times the area under the pink curve, which is 32 plus 75, while the expense is 3 times x1 dot square delta t plus x2 dot square delta t, where delta t is 0.5. Substituting x1 dot with q over 0.5 and x2 dot with 5 minus q over 0.5 gives 12q squared minus 60q plus 150. Subtracting the expense from the income, we obtain the profit as shown. Differentiating the profit with respect to q and set to 0, we have Q equals 3.75 and the maximum profit in this case is 93.75. Note that x1 dot equals 7.5 kilometers per hour and x2 dot equals 2.5 kilometers per hour. So the velocity in the first half is 3 times higher than the second half. We will come back to this special case a bit later, but for now, let's move on to another special case. Special case 2, Mr. Lagrange drove with constant acceleration. Again, let's compare the profit from the blue and the pink options. The top, middle, and bottom graphs show the position, velocity, and acceleration functions respectively. The acceleration of both options have same magnitude but opposite sign. The blue with positive acceleration and the pink with negative acceleration. Let's bring in graph of x dot squared. It can be observed that the area under the curve of x dot squared in both options are the same, and therefore their expenses are the same. However, according to the x-curves in the top graph, the area under the pink curve is higher than the area under the blue curve, so the pink has higher income and hence higher profit. Let's find the maximum profit in this case by first writing down the equation. X double dot equals a constant a, x dot equals v naught plus at, and x equals v naught t plus at squared over 2. Since at t equals 1 hour, x equals 5 kilometers, we have v naught equals 5 minus a over 2, which is substituted into the two equations below as shown. Replacing x and x dot in the profit equation at the top, we have the profit as a function of a as seen. Differentiating the profit with respect to a and set to 0, we have a equals negative 10 kilometers per hour square, and the maximum profit for this case is found to be $100. Now, do you think the profit can be over $100? It seems likely, right? Because there are infinite other kinds of curve we haven't tried yet. Let's try adding an extra term p into the equation of x, so x can be any function. The restriction is only that p of 0 equals p of 1 equals 0 to make sure that the initial and final conditions do not change. By adding the extra term into x, x dot and profit, we also have extra terms. Obviously, the extra term of x dot is just p dot, and the extra term for the profit is found to be minus 3 integral p dot squared dt from 0 to 1. This is the derivation of such extra term, which I will not go into details, but you can pause the video and take your time to follow the steps. Since this extra term of the profit cannot be positive, the profit cannot be over $100. We have proved that the maximum profit is $100, which corresponds to the graph of x being a concave down parabola. However, this is like cheating because we stumbled on the case of maximum profit, so this is largely down to luck. The question is whether there is a more direct proof. The answer is yes, and this is where calculus of variations comes in. To make things more intuitively, let's go back to special case 1. We are going to find the maximum profit for this case in a different way that we did before. First, assuming that the pink curve of x maximizes the profit, and defining big X as a function of the purple curve, which is similar to the pink curve but is lifted up by h at the midpoint. Now let P denotes the profit of the big X. We can see that P is maximum when h is 0, since when h is 0, big X becomes small x, which maximizes the profit. The income of the big X is 60 times the area under the purple curve, which can be divided into the green and the yellow area. Now 60 times the green area is the income of the small x, and the yellow area contains two triangular regions which base h and height 0.5, so the yellow area is 0.5 h, and when multiplied by 60 becomes 30 h. The expense of the big X can be expressed as the sum of two terms in which the first term is the expense of the small x and the second term is 12h times q minus r plus 12h squared. We can now express p as a function of h as shown. By differentiating p with respect to h and set to 0, we have q equals 3.75. You may remember from earlier that this leads to the profit of $93.75. You may not like this method as it is harder than the one we did before. However, the benefit of this method lies in its ability for generalization, as we will see shortly. You can see that the average rate of change of x dot is negative 10 kilometers per hour squared. If you recall that negative 10 kilometers per hour squared is also the acceleration in the case of the highest profit possible. Is this by chance or is there a pattern? Well, let's find out. Now, if we go further by allowing the velocity to be changed 3 times so that the curve is now a piecewise linear with 4 sections. Again, assuming that the pink curve of small x maximizes the profit. Let the purple curve of big X be similar to the pink curve but is lifted by h at t equals 0.25 hour. By performing the analogous analysis to the previous 2 section case, we find that the average rate of change of x dot around t equals 0.25 hour has to be, again, negative 10 kilometers per hour squared. This is also the case for the average rate of change of x dot around t equals 0.5 and t equals 0.75. We can see that to maximize the profit, the average rate of change of x dot between any 2 sections is required to be negative 10 kilometers per hour squared. It can be shown that this is always true for x with any number of sections. Subsequently, if we keep increasing the number of sections until infinity, the resulting curve will be continuous with x double dot being negative 10 kilometers per hour squared at every point, which, as we have seen before, lead to the maximum profit of $100, and that's the outline of our more graphical than analytical kind of proof. Now, if the number 60 in the integral were to be replaced by b and the number 3 by c, we would have x double dot equals minus b over 2c. This can be expressed mathematically as the definite integral bx minus cx dot squared will be maximized if x double dot equals minus b over 2c, or 2cx double dot equals minus b. Equivalently, we can say that the definite integral cx dot squared minus bx will be minimized if 2cx double dot equals minus b. Now it's time to turn our attention to Lagrangian mechanics, which is a formulation of classical mechanics based on principle of least action, which requires the object to take a path that minimizes a quantity known as action, denoted here by letter S, which is a definite integral of L, where L, which is called Lagrangian, equals the kinetic energy K minus the potential energy U. We can see that nature also plays the role of an optimizer, obviously not to maximize profit like us, but to make the average potential energy higher than the average kinetic energy as much as possible. Why? Just the way the nature is, I guess. For example, for a classical particle under uniform gravitational field, K equals 1/2 mx dot squared and U equals mgx. We can see that in this case, C equals 1/2 m and B equals mg. So the equation 2cx double dot equals minus b becomes x double dot equals minus g, which is consistent with Newton's second law. The green statement below can be generalized as the definite integral of k of x dot minus u of x is minimized if d by dt of dk by dx dot equals negative du by dx. Do you want to see the proof? Well, let's prove it then. But as a prelude, let's take a little detour by considering this question. What is the shortest path between 2 points? Well, any kid would know that the answer is a straight line, but try to tell that to a mathematician and they would demand a proof. So let's try to prove this. First, let x be a function with shortest path from a to b. Let's pretend that we are not quite sure that x is a straight line. Now let big X equal small x plus epsilon times h, where h of ta and h of tb are 0, so that big X and small x are at the same points at both ends. Of course, when epsilon is 0, the big X becomes small x. Now, let function a be an arc length of big X. We can see that the graph of a will be lowest when epsilon is 0, since that makes the big X to become small x, which has the shortest path. From the application of integration, the arc length formula is this. And so, this is a prime epsilon. By using Leibniz rule, we can move d by d epsilon inside the integral. After replacing big X by small x plus epsilon h, we have this. Consequently, we have a prime 0 equals definite integral of x dot h dot over square root of 1 plus x dot square. From the graph, a prime 0 is 0, and this would be the case if the entity in the pink area is a constant. This implies that x dot has to be a constant. Since a straight line has a constant slope, x would be a straight line, and that concludes our proof. Effectively, what we did is actually proving a special case of the green statement, in which k is square root 1 plus x dot squared and u is 0. I will leave for the viewer to work out that in this case, this equation is reduced to x dot being a constant, as expected. Now it's time to prove the green statement in general. Let x be a function that minimizes s, which equals definite integral of k of x dot minus u of x. Again, we let big X be small x plus epsilon times h, where h of ta and h of tb are 0. Then let's define a function a of epsilon as definite integral of k of big X dot minus u of big X, such that a of 0 is s. Like in the previous case, the graph of a would be lowest at epsilon being 0. Again, using Leibniz rule, we can express a prime epsilon like this, and after some work we obtain this. This looks quite complicated, but actually rather straightforward, so I will not go into details, but the keen viewer may want to pause the video to take a look for a bit. Now we have a prime 0 equals definite integral of dk by dx dot times h dot minus du by dx times h. By using the condition from the green statement, we can replace minus du by dx with d by dt of dk by dx dot. According to the product rule, we can see that the integrand can be expressed as d by dt of the product between dk by dx dot and the function h. Subsequently, it is direct to show that a prime 0 is 0, and that concludes our proof. Now let's get back to the Lagrangian mechanics. In the green statement below, from L equals k minus u, then dk by dx dot equals partial dl by dx dot, and negative du by dx equals partial dl by dx. So the equation in the statement can be re-expressed as time derivative of partial dl by dx dot equals partial dl by dx. This is called the Euler-Lagrange equation. For demonstration, let's apply this equation to a couple of well-known examples. The first one is a spring problem. If we pull the spring, it will stretch out, and if we let go, it will oscillate. The kinetic energy is 1/2 mx dot squared, the potential energy is 1/2 kx squared, and the Lagrangian is 1/2 mx dot squared minus 1/2 kx squared. From the Euler-Lagrange equation, we have d by dt of mx dot equals minus kx, or mx double dot equals minus kx, which can be written as x double dot plus k over m times x is 0. The solution of this differential equation of motion looks like this, and we can see that the spring will undergo a simple harmonic motion with angular frequency square root k over m. The next example is the pendulum problem. If we let the pivot point be at point 0, 0, and the location of the bob at point x, y, instead of solving for two variables x and y, we can choose to use the angle theta as the only variable. We can see that x equals r sine theta and y equals minus r cos theta. In this case, we need to generalize the Euler-Lagrange equation by replacing the variable x, which is a position, with q, which is a generalized coordinate. The displacement s is given by s equals r theta, and so the velocity v equals s dot equals r times theta dot. The kinetic energy is 1/2 mv squared equals 1/2 mr squared theta dot squared. The potential energy equals mgy equals negative mgr cos theta, and the Lagrangian as shown. Applying the Euler-Lagrange equation, we have the angular acceleration theta double dot equals negative g over r sine theta. Note that this differential equation of motion does not have closed form solution and needs to be solved numerically. Of course, the pendulum motion can be analyzed using Newton's law, but the force is required to be decomposed into tangential and radial components, and so it's not as nice and easy as using the Lagrangian method. Furthermore, for complicated systems like double pendulum, Lagrangian is a preferred method, although as you can see, it's still not that easy. Using Newton's law is virtually out of question as it is much less systematic and very messy. Well, I hope this video has some success in conveying the essence of calculus of variation and Lagrangian mechanics. I just want to add that not only is principle of least action widely used in classical mechanics, it also paved the path for Feynman to discover his path integral of formulation of quantum mechanics.
Lagrange is the name of a mechanic, but all he does is mathematics. His principle is the least action. Getting from A to B is not so fun. What is the integral of kinetics? Less potential that nature loves to dig. Perhaps it's the way the nature is. Otherwise the world wouldn't be like this.